Okay, so let's go. Thank you very much for being here today. So today, Olivier and myself will present a talk about hydrological modeling with R based on several works we've done in our team. So I'm a researcher at INRAE, which I will present just now, and Olivier is a data scientist and package developer in the same team. Next. Yeah, so the objective of our talk today is threefold. So first, we want to give an overview of the available packages in R that allow for hydrological modeling. And we worked on analyzing that on a modeler perspective, but also on a package user perspective. Then we will present two packages, airGR and airGRteaching, which we develop, and which propose the GR hydrological models. And finally, we'll give an overview of other packages that are around this airGR package to open new possibilities of modeling. So the outline of the talk is this one. So first I will present our team in a few words. Then I will present a work on the R packages that allow for hydrological modeling based on a paper. And Olivier will present the airGR main tools. And finally, I will finish with the airGR Galaxy. So our team, so we are a research center called INRAE, which stands for French National Research Institute for Agriculture, Food and Environment. And we are based in Antony. So Antony is very close to Paris. And INRAE is very large, so it's 12,000 people, many research units, and we are all around France. And so the topic of this institute are very large, climate change and risks, which are the ones we are focused on. Agroecology, biodiversity, food, health, bioeconomy, and everything around society and regional strategies. Regarding our team, the next slide, yeah, thank you. So we are 9 researchers or engineers, functionaries. We have a lot of PhD candidates, postdoc, fellows, engineers, and interns or visiting scientists. And our research objectives are around hydrological modeling. So first, to understand the behavior of catchments, both for natural conditions, which is what we have done on a historical point of view in our team, but also we are looking more on influenced hydrology. We try to develop models and methods for forecasting, for simulating stream flows, and we have a lot of works around uncertainties. We also have something which is very linked to Nance Ador's talk last month about large sample hydrology, meaning that we are methodologies on many catchments in order to have something that works on a very wide range of conditions. And finally, we do our research for operational applications, and it's also used for management, for engineering, which means that we try to turn feedback into research questions to improve our tools. So to summarize, our research topics are aggregated around 4 topics: forecasting, global change and impacts, regionalizations and variabilities, and hydrological modeling and uncertainties, with some keywords like risk, society, resources, and catchment. Okay, so now I'm going to start with the first scientific thing about hydrological modeling with R packages. Yeah, so actually, wait, the rationale around this presentation is that we have many R packages, like dozens of R packages available on the official repository. In 2019, with Louis Slater and colleagues, we made a paper in Hess, which we have in this slide, in which we tried to assess what is available in R for doing hydrology. So it relies on workshops we have done at EGU for years, and we analyze the main packages that are available for the main steps of the hydrological workflow, like preparing data, retrieving data on archives, hydrological modeling, and plots, analysis, and so on. But that's a lot of things, so we could not develop all the steps. That's why after that work we have done an additional work on hydrological modeling. So you all know that hundreds of models exist. There is a sentence saying that each modeler has its own hydrological model. That's almost true. And despite of all these models existing, only some are available in R. But still, we felt that there was a need for guidance in choosing a package around this 10 to 20 packages available. First, because not all hydrological models fit all your specific topic. Also because the packages present very different functionalities, and maybe the one you need is missing. And finally, we also knew that the documentation was very, very different between the packages, with some packages with very good documentation and some packages with no documentation at all. So in this work, we focused on the differences between the models. We analyzed the different model inputs necessary. We analyzed the documentation and also how the packages were implemented. And we also proposed very simple R codes as additional supplementary material to run these packages. So in this work, we will give an overview of the 8 models, in the 8 packages that propose hydrological models. And also we'll focus on the models that are available. But you will not get from this presentation how to run each single package or each single model. For this, you have to check the supplementary material of the paper. And also, we will not have time to provide an in-depth explanation of all hydrological models. So this is a paper led by Paul C. Astagneau. And for this work, we worked with an international team because we tried to contact the developers of the different packages to have the best information about each package and each model. And so I invite you to have a look after the talk at this paper. So here we'll focus on different things. So here are the 8 packages we analyzed. Yeah, what we have in this table is the name of the package and also the models that are proposed in this in each package. So for example, you can see that we have the GR models in 2 packages, airGR and Hydromod. You have the top model package, the top model in 2 packages, top model and Dynatop model. Also HPV is quite present in R in 2 packages, HPV.Yanigla, but also TUW model. And finally, you have some other models, IHACRES, IWBM, Sacramento, Walrus. And we also, we found these packages, but not only on the official R repository, which is represented by the R symbol here, but we also found some packages which were only on GitHub. And on the right column, you can see that not all packages propose no model. So that's a first way to decide which package to use. If you want to work on snowy basins, you can eliminate 2 of the packages. Yeah, so let's start with a modeler's perspective analysis. So here, yeah, you really have to think as a modeler what you want to represent in your basin. And the first thing that is obvious is if you have snow in your basin, you need a snow model, so which means that you can eliminate 2 packages. But the second step of analysis on this is that snow models that are present in the packages can be very different, especially on the way the processes are represented. Some were on representing snow processes with a degree day method. Other ones were based on the energy balance method. And the second point that is very important is a spatial resolution, because you all know that in mountainous areas, there is a very strong orographic gradient on temperature and precipitation. And here we represent 2 ways of representing the heterogeneity on basins. On the left, this is what we classically do with the GR models, meaning that we cut the basin with areas of different proportions, with the same proportion but different altitudes. But this is done in a very different way in other packages, where you can, for example, specify if I remember, you can specify the different altitudes. And also you have to know that in some packages, there is no spatial resolution in the snow model. So HBV, Anigla, Hydromad, and Walrus. Regarding the hydrological models, here you also have a very, very large diversity in what you have in these packages. As our packages are supposed to be simple tools, the models that are proposed are most of the time lumped, meaning that you represent the basin as a whole, with aggregating precipitation temperature data and simulating the discharge journey at the outlet. So this is the case for almost all packages, but some of them go further, like representing the basin with hydrological response units, HRUs. So this is the case of the DYNA top model, SAC, SMR top model, and TW model packages. You also have the possibility to have sub-basins, so semi-distributed modeling of the catchments. And you can also have a routing between HRUs or sub-basin. So this is also important in case you want to represent a distributed basin. Of course, all models can be very different. So we made some effort to represent the processes implemented in the different models with quite uniform representation. So this is what you have here. And this is a representation we already developed a couple of years before in the paper from Debourg Heuser in 2017. So I will not have time to go into details for each model, but what you have to see in these diagrams is that each box with a different color represents a different process, like snow interception, quick runoff, groundwater, and so on. Each arrow is a flux, and you have the description of how the total stream flow is obtained from the different compartments of the model. So for example, if I focus on walrus, you can see that groundwater is very important, and the reason why it is the case is because walrus was developed for lowland basin in the Netherlands. So of course, if you want to work on a very responsive basin with intense rainfall, maybe walrus is not the best solution. So this is a way to help people understanding the different models available and make a choice on the package they will pick. Now, from a package user perspective, we made a couple of additional analysis on different with different indicators. What is important is, of course, the inputs. So not all models need the same inputs, even if all need precipitation and potential evapotranspiration. Some of them need digital elevation models or the soil type. And if you don't have this data, you cannot use these packages. So we try to put this information into a simple table. And also the time step available for a different proposed model is very important, because if you want to work on flash flood and the model only works on a daily or monthly time step, it will not be the best choice for you. So you need to focus only on the models working on very fine time step. And last, on the right column, you have the number of parameters to optimize, which can be quite important because the more parameters you have, the more difficult it is to find the optimal parameter set. And also, of course, all models propose as an output the simulated discharge, but some packages also propose additional time series of internal fluxes or other compartments. So TS in this table stands for time series, AET is actual evapotranspiration, and RC is a runoff component. So, for example, you can see that the SAC SMA-R package does not propose anything else than discharge as an output. So, if you want anything else, this will not be your solution. But you can see that if you want to have access to internal fluxes, then you do not have a very large choice, because when there is a till in the table, it means that you only have a couple of internal fluxes. So this can also guide your choice on the package or model you want to use. And in addition, the packages propose different functionalities. Of course, the basis is to have the hydrological model. But as I said, based on our first analysis on the Slater et al. Paper, you need more. You need to prepare data. You can be happy to have access to criterion computation to assess the quality of your simulation. You can need a calibration algorithm. Sometimes it's quite difficult to make plots, so you can be very happy to have very basic plots in the package. You maybe want to have access to a guide, so a GUI, an interface to manipulate the model, to do some preliminary tests before doing your modeling. And also maybe you want to work only on snow without going down to discharge. So some packages propose that, but not all of them. So this kind of table also shows what you can expect in the package before choosing one of them. Okay, we also propose very, very complex diagrams here that I will not present into details. So this is really useful if you start using the package. So no worries if you don't understand that. Here, it's just for each package, we described we put the names of the functions that you need to use to make a complete modeling exercise, from data preparation to modeling and to the analysis of the outputs. Why did we do that? It's because the more you can tune your modeling exercise, the more functions you will need. But still, it's not very easy always to understand which function to use first, and then which one you need to use, and so on. And it can be very difficult to understand the relationship between the different functions. So with this kind of graph, we hope that it's a bit more easy to understand, and we try to put some different colors for the modeling step, data preparation, parameter estimation, simulation, and so on. So I will not say more about this here because it's only needed when you start using the packages. And finally, of course, we did some analysis of how fast the different packages are. Why did we do that? Because not all packages only include R code. So something nice with R, you can also use different programming languages, and especially some of them that can be compiled can be quicker to execute, which is very important when you want to do multiple runs of your models. So for uncertainty analysis, or also for calibration. So here we made many computations on the different models and the different packages, and we did that for mountainous catchment in blue-green, and we also did that for midland catchment in orange. So the difference between the two is that you have a snow model or not. And here you can see that you have a very large a panel of computation time. So depending on the number of catchments you have, or the modeling you want to do, this might guide your choice also. Because for some packages that need many seconds to do one run, if you want to do a very complex, for example, Monte Carlo analysis, it might be more difficult. And so this is where we have put the codes to run the different models, the different packages, sorry. So it's these are very simple codes just to prepare data to make a run. We did not include in these codes the calibration of the parameters after many discussions with our colleagues. And the main reason why we did that is because the calibration of parameters is something that has to be decided by users based on what they want to do and the problems they have. And there is no global solution that might be applied in every case. And yeah, to finish, to open a bit more the landscape around that, we can also check what we call a task view in the Coron website, because we have a hydrological task view. So a task view is something that it's a list of packages around the topic, and in this task view you have a quite complete and updated list of packages around hydrological modeling or hydrological data and everything that goes around that. So it can be a very interesting source of information for you also.
And now we will focus on airGR main tools. So the objective of these tools, there are many objectives. To have a model core in Fortran, the goal to have a code in Fortran is to have a speed, to ensure speed computation and a consistency with the development history of the GR model. And to use a more flexible language than the Fortran for additional functionalities. And to have a tool that is free, open source, and easy to disseminate. That's why we decide to develop the airGR package. And we want to offer a standard version of the different model we developed. So that's why we developed many tools. You can see on this graph. I will focus in the first time to airGR and airGRteaching, which are our packages. And we have also a graphical user interface, which are available on a Sunshine INRAE website. So let's go on airGR and airGRteaching. These tools are quite similar, but adapted to individual needs. So airGRteaching is designed to facilitate the use of the models by people which are unfamiliar with computer programming, and it offers turnkey tools. So it's developed especially for students. And airGR is designed to allow great flexibility of use and offer more advanced modeling options. But in fact, you have to keep in mind that airGR and airGRteaching offer the same hydrological models, but in fact, they differ just in their implementation and their manner to use. About the community of the airGR packages. So the people who use these packages work in public or private sectors as research and education, as a university, research centers, and so on. Also state services as meteorological services, environmental services, and so on. And consultants, energy producer, insurers. So you can see on the map that it's about only the airGR package, which is used on all continents. And we have counts more than 200 locations as university, research center, and so on, who use airGR, more than 60 countries, and currently there are more than 100 scientific articles who use airGR. And airGRteaching, as it's developed for teaching hydrological modeling, it's less used, and we count 13 locations as universities and engineering school in France, United Kingdom, Italy, and Kenya who use this package. I will focus on available features. So the embedded features are the suite of the GR rainfall-runoff models. I will present them just after. A snow model called CManage, a calibration algorithm, efficiency criteria, and data processing and display tools. As I said previously, the type of implementation, so the package are in R, but they're embedded, they are linked, they are interfaced with Fortran code to ensure quickness and yeah. The model available, so as I said, there is CManage, so it's a degree day model to simulate snow accumulation and melting model. There is a simple version in airGR, but there is also a version which allows to use satellite data as the MODIS data, for example. And in the suite of models, there are 7 lumped hydrological models from the yearly to the hourly time step So there is an annual model called GR1A with one parameter only. Monthly model, 3 daily models. So the most famous is GR4J, but you can see that there are GR5J and GR6J, which are more useful to simulate low flows, and 2 early models, GR4H and GR5H. And the daily and the early models can be coupled with the snow model Semanage. The available criterion are these ones. So the root mean square error, the Nash and Sutcliffe efficiency criterion, the Kling and Gupta efficiency criterion, the modified version of the KGE, and it's also possible to customize a composite criterion mixing different criteria and different stream flow transformations. We give with the package an algorithm to calibrate the model. So it's a step-by-step method developed at INRAE, but it's also possible to couple some other methods as MCMC or and so on methods. I will not detail all these tables, but you can see here the different options you can use with the different packages. airGRteaching allowed to launch a graphical user interface, but there is also a version with only simple codes. And airGR is more complete, but more difficult to use because there are many options. So that's why the graphical user interface allows to use less options, and airGR is a more complete tools to use. But in any case, the data required by the models are the same, and there are very few. You need some observed hydrometeorological records. So you need the dates and the times. So in R, it's in the POSIX-T format, and it depends of your model, but you need to have yearly, monthly, daily, or hourly time step, depending of if you use GR4J or GR1A. You need obviously the average precipitation on the catchment in millimeters, the potential evapotranspiration on the catchment, and if you want to calibrate your model, you need the stream flow, all in millimeters. You can see that you have an additional column with the temperature. It's when you use the Semanage model. And if you want to activate the snow model, you need the elevation percentiles of your catchment. And that's it. So these data are required for airGRteaching and airGR because they allow us to use exactly the same models, as I said previously. So I will focus in first time to the graphical user interface of airGRteaching. So in this case, you just need to launch one function, and it will open in the browser the graphical user interface. You have some dynamic graphic where you can zoom on. It's only possible to use in this interface the monthly and the daily models, not the early models, not a semi-distributed version of the models. So it's quite limited. The data needed are exactly the same I present previously. So the dates, the precipitation, the potential evapotranspiration, and the stream flow. And as I said, you need only to use one function to launch the graphical user interface. This function is called ChineGR. And you need to put your time series and to set the period you want to simulate on. You have a screenshot here of the graphical user interface. I will detail it just after. If you want to activate the snow model, you need the hypsometric data, the average altitude of the temperature and the precipitations, and the number of layers to compute the snow model. So here you have a screenshot of the graphical user interface. So it's open in your browser. There is also a demo interface available on the web. As you launch it from R, you can put your own data without any problems. You can see here on the left a panel where you choose your catchment if you have a list of time series. You can choose your model between the daily and the monthly model, and you can activate or not the snow model. You can set the different parameter value, and it changes on the central panel. So on the central panel, you can see the time series of stream flows and precipitation. So in black, it is observed stream flows, and in red, the simulated one. So if you move the slider on the left panel, it will change the simulated stream flow, so you can see in real time the effect, the different parameters. Besides, you have the error of the model on each time step. On the right, you have the criterion values of the NASH and the KGE on the display time series. So you can simulate the stream flow. It's also possible to calibrate the model. So on the left, you have the green button. And if you click on this button, you can calibrate the model using a setting objective function. So you can choose between the NASH and the KGE. And you can apply it on raw stream flows or on transformed stream flow as the square root stream flows, for example. So this is the main panel. You have also different graphics. So you can analyze your results displaying the regime of the precipitation as the stream flows, the relation between the simulated and the observed flows, and also the stream flows ordered by value. So you can see if your model is quite correct or not with this graphical output and with the criterion on the right panel. You can also have a look of the state variables of the models as store levels and the different fluxes. And finally, it's also possible to have a look of the different fluxes inside the diagram of the model. And you can see here the prediction store and the routing store at setting date. If you have some French catchment, it's also possible to have an overview of a summary of the data. So it's a graphical overview, but it's only available for French official database. And that's it. So you can launch this graphical user interface from R, or there is a demo on the web with currently with 2 catchment time series. It's also possible to run airGRteaching using very simple code. So you need exactly the same data. And there is one function to prepare the data. So you give your time series and you set the model you want to use and if you want to use the snow model or not. So it's the prep-gr function. After that, it's the same. If you want to apply the snow model, you need the hypsometric data. You can have a look on your time series just using the plot function on the output of the prep-gr function. So it's a static one. It's also possible to have a dynamic one and to zoom on and to move the mouse on and to read the values of the data. And after that, you can calibrate your model using the cal-gr function. So you give the output of the prep-gr, you choose the criterion you want, the transformation of the stream flow you want. You can set a warm-up period and you have to set a simulated period. And in 1 second, you have the result of your calibration. So we have the set of the parameters and the value of your criterion. You can also have some graphical outputs as the evolution of the parameter during the iteration of the calibration. You can have a summary plot to analyze the calibration results. And you can also display the time series with static or dynamic graphics. If you want to evaluate your model on another period, you can use the simgr function. You give the time series, the set of parameters you want to test, and you can simulate your stream flows. And you can evaluate it choosing your criterion and your transformation as previously. And you also have some graphical outputs. I will not detail all the functions of the airGR package because there are too many functions, but I just want to focus on the fact that you can have the most options using this one. So you can, for example, use satellite data, which is not the case using airGRteaching. You can choose the initialization of internal states using this package. You can define your composite criterion to calibrate the model. You can calculate a criteria over a discontinuous period, and so on. So it's a more complete tools. And just to display all the links of the function, there is this graph to explain all the link between the features. So you can see that there is more function as in airGRteaching. So when you start, you can use airGRteaching, which is more simple, and you can use it with all the GR models. So it's quite easy to take in hand, and it may be more easy to start with GR models. And it's also possible to have some tutorials available on the web to, for example, to couple another algorithm to calibrate your model as MCSE, for example, to use a semi-distributed version of GR models and so on. So you can have a look on these two websites to get some additional tutorials and to keeping updated of the news of the package.
Thank you, Olivier. So just to finish, we'll see a couple of other tools. So the first one is airGR data sim. So So this is airGRteaching, sorry. So this package is for data simulation of stream flow within different GR models. So this is a package that was implemented by Olivier and Gaia Piazzi, which is on the Coron, and we have a paper about the methodology that we put into the package, which is this one in WRR. So this package proposes two methods for sequential data simulation. So what is data simulation? It's a way to constrain simulation of models based on information you have, so observed data. And the methods we used are ensemble data simulation method, meaning that so this is what you have on the graph. So you have the gray arrows with different simulations, different members. You arrive at a time step where you have an observation here in orange with a uncertainty range. And so you compare your simulations to that, which gives you an updated ensemble of starting point for the next time step, which are the red boxes. And you propagate this initial state to the next time step where you have observed data. So this is very important for hydrological forecasting. So this is a basic methodology. What we propose in the package are data simulation methods that work for 3 daily models, GR4J, GR5J, GR6J. We have two very classical data simulation methods, the ensemble Cameron filter, but also the particle filter. What we can assimilate is observed stream flow. And to perform the data simulation, we have some procedures for perturbating different things. So first of all, meteorological forcing, which is a main uncertainty. So you can perturb precipitation and potential evapotranspiration. But you can also perturb model states. So the different stores in the model of the unit hydrographs. So the second package we wanted to present is airGR IWRM. So IWRM stands for Integrated Water Resources Management. So this is also a package that we have on the Coron, developed by a colleague of us, David Dorshi, which actually uses airGR but adds a layer around it to ease its use for semi-distributed modeling, because performing semi-distributed modeling when you have one or two basins upstream is quite easy with airGR, but when you have a very large basin with 100 of catchment flowing into the others, it can become very difficult to cut that. In this package, we propose a way to just fill in a data frame and it runs the different functions in the correct order. The second advantage of this package is regarding human influences. That's why we have integrated water resources management in the name of the package. So we can do two different things, integrating uses that we know, observed uses. So you can inject that or withdraw water directly somewhere in the basin where the influence is. But you can also implement water uses models and the way the uses are managed if you have a reservoir and so on. So this is very useful for climate change and adaptation methods. So to go into more details, what you have in airGR is a very simple way to go from upstream to downstream with a lag model in the GR models. And what airGR proposes is to automate the way the semi-distributed network is handled. So this is what you have on the bottom of the slide. On each upstream catchment, you run a GR model, and you take the simulated discharge and you lag it to the output to the outlet of the downstream catchment, and you add the simulation of the downstream part of the catchment to have the total stream flow flowing out of the catchment. So you just have to add the one function to run this. This is an example of what you can get from running this package. So here we are in the Seine basin. So the Seine is a river flowing through Paris. Very upstream to Paris, you have a very, very large reservoirs that aim both at mitigating flows and also low flows. So two different, two opposite objectives. And we are lucky we have very long time series here. And for example, for one tributary, we have data before and after the building of two reservoirs. So you can see on the top picture that you can represent well the time series before the construction in 1990. But after the construction, just running a GR model is not enough because the seasonal cycle is modified a lot. And if you plot the seasonal cycle, you can see that very easily. You overestimate floods and you underestimate low flows because you don't take into account the reservoir. But if you use airGRteaching and take into account the reservoir, which is the bottom part of the slide, you see that both regime, the discharge regime, but also the time series of stream flow simulated after 1919 are very well represented. Then we have a very, very new package, airGR datasets, which is a package that actually proposes a set of data. So we proposed hydrometeorological data for 19 catchments in a lumped way at a daily time step, and all the metadata that you need to make anything with that. So you have precipitation, temperature, potential output, concentration, and discharge mainly. So this is all available on the Coron. Actually, I think that it's not coming soon, but available for a couple of days now. We are very happy about that. And yeah, a few words about the future development we want to make with different packages. Things that we don't have yet, but almost, like linking the snow model semanage to the monthly GR2M model. We also want to improve the link between the snow model and hourly models because it's a very complex relationship. So we're working on that. Also for flash floods, we have some PhD works ongoing and almost finished to improve our hourly models, in which the students added some intensity function to better represent Hartonian runoff. We also have an interception turn GR5H. We want to add it in GR4H. So very, very minor things, but that can be very useful. Regarding the routing functions, so the lag functions from upstream to downstream, we want to propose something else than the simple lag that we have for the moment. And yeah, it's ongoing. We want to continue to add the PhD research. So this was all in the airGR package. Regarding airGRteaching, we recently integrated a way to use engaged stations in the network, because the classical way to implement semi-distributed models is to cut the basin on points where you have observed discharge data, but sometimes you have some interest within the catchments or subcatchments. So you want to do simulations, but for this you need a way to propose parameters to the model for these engaged stations. Sorry. We also want to provide libraries or what we call vignettes, so this very complete description of functions to represent different type of influences, because when you don't have the observed influence data, you want to represent it. And also we are working on an article about this package, which will come soon, I hope. And finally, airGRteaching. Using the airGR dataset, which proposes data for many catchments, we implemented in the coming soon version of the package some exercises which can be used for teaching hydrology, for master project, and so on. So this will come very soon, and what will come also very soon, I think it can be submitted in the next before the end of the month, is an article describing both the use and the content of the airGRteaching package, but also describing some very general modeling, hydrological modeling exercises, but also some very specific exercises that can be used for teaching. And one more, airGR Plus. So this is the next generation package in which we want to use. We want to add many hydrological models different than the GR models, but within the way we propose the GR models. So this is mainly based on the work by Charles Perrin in the early 2000s, because he implemented different very classical models like top model IRCS, HPV, Sacramento, or Tank. He implemented these models in a lumped way, and we want to put that into a package. So we hope to see that coming on the Coron next year. And I think that's it. So we are open to questions or discussions. So thanks a lot for listening to us, and very sorry for the French accent. I hope you understand.